Welcome back. Earlier, we defined the discount factor as conversion vector can convert the present value, future value, and annuity value of cash. We can see that discount values are a very powerful tool in calculations, as illustrated in the 3 examples in this video. In this example, we will use discount factors to calculate the interest rate. Given a discrete cash flow diagram from the bank's point of view, what is the interest rate that the bank is charging for this loan? So the bank initially has a negative value of 10,000, which means that the bank loans the loaner $10,000. And then in a consecutive 36 months, so this is compounded monthly, the bank was paid back each month $320. Because it is consecutive and n equals to 36 months, and this gives us this annuity. A equals 320. And then it was paid. The initial loan that the bank gave was 10,000. That is the present value of the loan. What we want is the interest rate. What we know is n equals to 36. Already know. To do this, we can use the discount factor, either A over P or P over A. So the discount factor for A over P equals to I times 1 plus I to the nth divided by 1 plus I to the nth minus 1. We are given A, which is 320 per month, and then P is 10,000. Equals to what we want to solve for is I, and then n is compounded for 36 months. Notice that the interest rate that we're calculating here is the monthly interest rate, not yearly. You must be careful because n is base. And to solve this, we cannot use analytical method. We need to use numerical methods using a graphing calculator. Let's use the graphing calculator. When using graphing calculator, we'll put in the raw equation so that we can see the symbols and ensure that we have not typed wrong anything. And these symbols, we can plug in numbers. And we want to equate the right side of the discount factor to the left side of the discount factor, which we have known values. So I is a thing that we want to calculate, so we set it as x. And n is 36 months that we consecutively paying back the loan to the bank. A is the annuity, which is 320. P is the present value, 10,000. Then we want to equate these equations, so we want to find the point where y equals to a divided by p intersects this curve. So zoom into here, find the intersection, which is 0.00786. And therefore, we have calculated a monthly interest rate of 0.006, which is, if we do the calculation, is 0.786% monthly. And to get the yearly interest rate, we'll multiply by 12 times 0.786%, and we will have 9.432. And we should probably round it with significant figure. 9.4% annual interest. This example, we will use discount factor to calculate the future value. In this example, money is invested in the saving account that pays a nominal interest rate of 6% per annum compounded monthly. So the interest rate is 6%, is an annual, goes to 0.06, and compounded monthly. So this we have on the cash flow. The account is opened with a deposit of 1,000 here initially, and then deposits $50 for each month that are made for a period of 2 months. This is for 24 months, 2 years. This is 24 months, followed by a monthly deposit of $100 for 3 years. 3 times 12 is 36 months. That the value of, what is the value of the saving account at the end of the 5-year period? So we're asked to find the future value. And we have a present value of 1,000 initially, and then 2 annuity, because we have a consecutive uniform payment for 24 months and for 36 months. We can break it down into 3 segments. First segment is the initial deposit. The second segment is the annuity for 2 years, which is 24 months. And the third part is the annuity for 3 years, or 36 months. There are many ways to approach this problem. For example, one approach is to, for each month, we will look at its final value. Then for each of these, we will calculate the time value of them. Calculate the first month, calculate the second month, and then add them up and calculate all 60 months value. However, that is not a greatest approach if we want to do it by hand, because then we will add up 60 more future values, and that is not ideal. That could probably be done by computers, but for hand and paper calculations, we won't do that. A more effective way to solve this problem is to conquer it by parts. For example, we can look at the first part to calculate the future value of the deposit. The deposit is in a total of 60 months. So the present value for the deposit is $1,000. And then it is deposited for 60 months, so n equals to 60. So the future value is equal to the present value multiplied by its discount factor, which is f divided by p. And f divided by p can be found in table 9.1, which is just compound interest. 1 plus I, the nth. But notice that here we have n is in month, but I is in year. So we want to convert the interest to monthly interest from yearly interest. So that is the yearly interest divided by 12, which is 0.06 divided by 12 is 0.005. So we can plug in numbers. 1,000 plus the monthly interest to the power of the amount of months that it is compounded. And it can be calculated with numerical value. And for the second part, we see that this is a constant value of uniform cash exchange here with the consecutive months. So we have an annuity of $50. We want to select this time, the final time 60 months as a final value. But we can solve this problem by first calculating the value of annuity at the 24 months where it has stopped being an annuity, and then compound them over the rest of 36 months. Step A is to calculate annuity's future value at 24 months. That future value equals to annuity multiplied by its discount factor, f divided by a. And f divided by a can be found in table 9.1, which is 1 plus I, the nth minus 1 divided by I. And we can substitute numbers for that. And then from that, we can calculate future values for 60 months at 60 months. So that will be the present value, 24 months. Suppose we're at that. So this is the present value at 24 months. Multiplied by its discount factor, which is the future value divided by the present value. And future divided by present is just compound interest. F at 24 months multiplied by 1 plus I to the nth found in the table. So you can substitute things in. We have a 1 plus I to the nth minus 1 divided by I multiplied by 1 plus I. And this can be calculated with a numeric. And the third part is this 36 months of a constant uniform cash transaction with consecutive 36 months. So it is another annuity with value of $100 per month with 36 months. And the end point is also 60 years. So the future value at 60 months, and the future value at 60 months is equal to the annuity times its discount factor, f divided by a, which can be found in the table. So we have 1 plus I to the nth minus 1 I, 1 plus I to the nth. And notice that this n is now 36, and not to be confused with this n, which has 24. N1 is 24 and N2 equals to 36. So the first part we use N1 and the second part we use N2. Because the first part accounts for the annuity and the second part accounts for compound interest. And finally, we will add them up. So the total amount of future value will be F1 plus F2 plus F3. And the calculated numerical value for is 6,800. Another way to look at this problem is that first part is the same. We have the deposit of present value of 1,000 that has months of 60 months. And then the yearly interest rate is 6%, so the monthly interest rate can be calculated from yearly interest rate. And then we can get the future value equals present value times the discount factor, which is compound interest. And this can be calculated with a numerical value. First part is the same. But the second part is a little bit different. Second part, if we look at this, we can divide it into this constant section. So from here to here, it is always 50. Here to here is 50. So the second part now interested in is this part. This part is and this part is the third part. So now we have an annuity of $50 for a total of 60 months. Annuity is $50 and the amount of time is 60 months, because we look at things below this line, this is a constant cash transaction at $50. So if I redraw the cash diagram to two parts, it will be constant 50 for 60 months, 1 to 60, plus an additional 1 to 60, and at 24 months, I have uniform cash transaction $50. And add them up, we have $50 in the initial 24 months and $100 in the final 36. So we're breaking them down to part 2 and part. So for part 2, we have annuity of $50, and then months is 60. So the future value is equal to annuity times its discount factor, F over A. And from the table is A times F over A equals to 1 plus I, nth minus 1 divided by I. And this can be plugged in, which is 50 times 1 plus 0.5005, 60 months divided by monthly interest rate. And the third part is the final 36 months where we have annuity $50, but it will just be 36 months of annuity. So same equation applies, but the values of each variable we substitute might be different. So A still is 50, 1 plus I is still the monthly interest. The number of months we're compounding is 36 months. And finally, we add everything up. F equals to 1, 2, 3. I label them away. Then we will still get the same number of final result, which is 6,800. Please verify using your calculator. Let's look at another example that calculates interest rate and future values using discount factor. Example is an investment plan that involves investing constant $8,000 per year, 40 years, leading to retirement. This is a constant value with consecutive years, meaning this is an annuity. And then the plan then provides this amount of money for 20 years, retirement income. After those 40 years, they will pay you back. So this is another constant value with consecutive years. This is another annuity. The question is, what is the yearly interest rate used in this evaluation? First, let us draw a cash flow diagram. For the first 40 years, you are investing. So the money you're just flowing out for all 40 years. And for the next 20 years, you were paid back. This does not look to be in the scale, so I will dashes. And I will pay you back for 20 years. Okay. And the key point is that the value at initial 20 years, this point, at the point where you have retired, the value of all the initial stuff is equal to the value of the future stuff you will get at the point of retirement. So that translates into the future value at 40 years of all this money you invested is equal to the present money, the present value, the annuity that you will get after your retirement. And to do that, the future value of the 40 years of annuity can be calculated by equals to annuity times its discount factor, FA. The discount factor can be found in table 9.1. So that is F over A is equal to 1 plus I to the nth minus 1 divided by I. In this case, we have an annuity of $8,000. We have an interest rate that is unknown. We have n equals to compounded for 40 years. So the interest rate we're calculating is an annual interest. And then at the other side, we have P, which is the present value of the 20 years of annuity after retirement. So that will be annuity F divided by A, which is a P divided by A as the discount factor, because we're converting from P, present value, P divided by here to here. So P divided by A, we look at the table 9.1, P divided by A is 1 plus I to the nth minus 1 divided by I, 1 plus I. To distinguish these two A's, I will put A1, A2 at the right hand. For the retirement, after retirement, the value is A2, annuity is 1067. Present value here. Interest rate is unknown, and the interest rate is the same as before, and number of years, 20 years. So now we can solve this using numerical method, plotting. Let's do that. Solve it with the graphing calculator. We want the left side to equal the right side. So we have the left side A1, 1 plus I to the nth minus 1, that divided by it. And on the right side we have A2 times 1 plus I to the nth minus 1 divided by I times 1 plus I to the n. And we note that the n is also different, n1 and n. Plug in all the variables. So for A1 we have annuity of 8,000. Years is 40 years. And A2 is 106667. I is unknown, so X. And the N2 is 20 years. And we want to find the intersection. We want to find the intersection between these two. To do that, we can go to change the axes. So the interest rate should be between 0 and 1. The y-axis is greater than 0. And go and find the intersection. Maybe this is too large. 5. The intersection here, we can interest rate should be 0.0596. The intersecting point has the value that's given by. And therefore, we have an interest rate of I equals to 0.059. And remember, we have n should be distinguished n1 and n2. The 42nd question, and this can be converted to percentage, around 6. Probably how much money can be invested in the retirement plan before withdrawal begins. So that is asked. First 40 years, what is the future value at 40? From the graph, we can see this line has an intersection value of this. This is exactly what we wanted. 3 times 10 to the $6. Or we can verify using calculation where F40 equals to what we have already calculated here. A1, 1 plus I to the n, 1 minus 1 divided by I, where A1 is equal to 8,000. I we just calculated, and N1 is 40 years. Then we substitute in the calculator, and we can find the same value, 1.3 times 10 to the. In this video, we walk through 3 examples of using discount factors to calculate interest rate and future value. So we're utilizing the property of discount factor as a conversion factor between the present, future, and